Hello everyone and welcome back to part 2 of our lecture on sample size determination. In part 1 we discussed what sample size means, why it matters and the different factors that influence sample size such as population size, confidence level, margin of error, population variability, research design, sampling technique, budget and time. In this part we will move from concept to actual sample size calculation. We will learn three commonly encountered approaches: Slovin's formula, Cochran formula, and the Krejcie and Morgan table. Most importantly, we will not simply memorize formula, we will understand what each formula means, when it should be used, how to calculate sample size step by step, and which method is more appropriate for a particular research study. So, without further delay, let's get started. Learning objectives. By the end of this lecture, you should be able to independently calculate sample size using the method discussed today. First, we will understand Slovin's formula through a numerical example. Then we will move to Cochran formula, which is more statistically detailed because it incorporates confidence level, population variability and margin of error. We will calculate Cochran's sample size for a large population and then learn how to adjust it when the population is finite using the Finite Population Correction or FPC. After that, we will learn how to use the Krejcie and Morgan table without performing lengthy calculations. Finally, we will compare these approaches and discuss which method you should use in your own thesis or research paper. Basic sample size formulas. Before starting the individual formula, it is important to understand that there is no universal formula that should be applied to every research study. Different methods make different assumptions and require different information. Slovin's formula is very simple and requires population size and margin of error. Cochran formula is more statistically rigorous because it incorporates the confidence level, margin of error and population variability. The Krejcie and Morgan table provide ready-made sample size for different population sizes. So, researchers do not need to perform the calculation manually. Therefore, researchers should not select a formula simply because it is easy. The formula should be selected according to the research design, population characteristics, sampling approach and statistical requirement. Let's begin with Slovin's formula. The formula is n equals to n divided by 1 plus n multiplied by e squared. Here n represents the required sample size. Capital N represent the total population size and E represent the margin of error, which must be expressed as a decimal. For example, if our population is 10,000 and we want a 5% margin of error, then we convert 5% into decimal form, which is 0.05. One important point for a student is that E must be squared in the formula. Therefore, 0.05 becomes 0.0025. Now let's calculate these examples step by step. Let's solve this step by step. Our population size is 10,000 and our margin of error is 5%. First, square the margin of error. 0.05 squared equal to 0.0025. Now substitute this value into the formula. The numerator is 10,000. In the denominator, we have 1 plus 10,000 multiplied by 0.0025. 10,000 multiplied by 0.0025 equal to 25. Therefore, the denominator becomes 1 plus 25, which equal to 26. Finally, 10,000 divided by 26 gives approximately 384.62. Because sample size must normally be expressed as a whole number, we round up to 385 respondents. So, according to Slovin's formula, the researcher should target approximately 385 respondents. Slovin's formula advantages and limitations. Slovin's formula has become popular mainly because it is very simple. A researcher needs only two major pieces of information. The first is population size and the second is desired margin of error. This makes it particularly convenient for students and researchers who are conducting basic descriptive survey. However, there are important limitations. The formula does not explicitly include a confidence level. It also does not explicitly account for population variability. Therefore, if your research requires a statistically rigorous justification of sample size, especially for complex inferential analysis, Slovin's formula may not be the strongest choice. Another important academic point is that the original authorship of Slovin's formula is not clearly documented in a widely verifiable primary statistical publication. Therefore, researchers should be cautious about presenting it as a universally accepted statistical standard. Cochran Formula for large or infinite population. Now let's move to a more statistically rigorous approach, which is Cochran Formula. The formula for a large or effectively infinite population is small n0 equal to z squared multiplied by a p multiplied by q divided by e squared. Here, z represents the z value corresponding to the selected confidence level, as shown in table. If confidence level is 90%, z value is 1.645. If confidence level is 95%, z value is 1.96. If it is 99%, the z value is 2.576. For example, at a 95% confidence level, z is 1.96. P represents the estimated proportion of the population possessing the characteristics being studied. Q is calculated as 1 minus P. Finally, E represents the margin of error. One important point is that if the researcher does not have prior information about population proportion, P is commonly taken as 0.50. This produces the maximum variability and therefore gives a conservative sample size estimate. Let's calculate Cochran formula using a standard example. Suppose we want 95% confidence level and 5% margin of error. Therefore, Z is 1.96 as shown in table. Because population proportion is unknown, we take P as 0.50 and Q as a 0.50. Now substitute all value into the formula. We get 1.96 squared multiplied by 0.50 multiplied by 0.50 divided by 0.50. Divided by 0.05 squared. The result is 384.16. Since we cannot collect data from 0.16 of a person, we round the result upward. Therefore, the required sample size is approximately 385 respondents. This is the commonly observed sample size of approximately 384 or 385 for a large population, when researchers use 95% confidence and a 5% margin of error with P equal to 0.50. What if population is small or null? Now we come to an important concept. What happens if our population is not extremely large? Suppose Cochran formula gives us initial sample size of approximately 385, but our actual population contains only 1000 individuals. In this situation, using 385 respondents may be more than necessary. Therefore, we apply the finite population correction, commonly abbreviated as FPC. The FPC adjusts the initial Cochran sample size according to the actual population size. The formula is N equals to n0 divided by 1 plus n0 minus 1 divided by capital N. Here small n is the adjusted sample size, n0 is the initial Cochran sample size, and capital N is the total population size. मीन्स अगर आपकी पॉपुलेशन लार्ज है और इनफाइनाइट है तो आप प्रीवियस फॉर्मूला का यूज़ करोगे, राइट लेकिन अगर आपकी पॉपुलेशन नोन है और स्मॉल है तो आप फाइनाइट पॉपुलेशन करेक्शन यानी कि ये फॉर्मूला यूज़ करोगे. लेट्स अंडरस्टैंड दिस विद एन एग्जाम्पल. राइट, आवर इनिशियल कोक्रोन सैम्पल साइज इज 384. नाउ assume that the total population is only 1000 individual and we substitute this value into the FPC formula. राइट, जो हमारा इनिशियल सैम्पल साइज था यानी कि n0 की वैल्यू थी वो हमें ऑलरेडी गिवन थी 384 या 385, जो कि हमने कोक्रोन 1977 यानी कि प्रीवियस लार्ज पॉपुलेशन के लिए जो फॉर्मूला पढ़ा था उससे निकाली थी, कैलकुलेट करी थी. पॉपुलेशन हमें कितनी गिवन थी 1000. अब इन वैल्यूज़ को अगर हम FPC यानी कि फॉर्मूला में पुट करते हैं 384.16 डिवाइडेड बाय 1 प्लस 384.16 माइनस 1 अपॉन 1000, तो हमें क्या रिजल्ट मिलता है 277. यानी कि फाइनल सैंपल कितने का होगा हमारा 278 का, अगर हमारी पॉपुलेशन का साइज़ क्या है स्मॉल है और नोन है. तो कॉकरॉन के अकॉर्डिंग सैंपल साइज जो रिक्वायर्ड सैंपल साइज है वो क्या होगा 278 रिस्पोंडेंट. स्लोविन्स वर्सेस कॉकरेन. Let's compare Slovin's and Cochran approaches. Slovin's formula is easier to calculate because it requires very limited information. However, it does not explicitly incorporate confidence level or population variability. Cochran formula is slightly more complicated, but it gives the researcher greater control over the statistical assumptions. It explicitly incorporates the confidence level, margin of error, and population variability. Therefore, when statistical rigor is important, Cochran formula is generally preferable. However, this does not mean that Cochran should automatically be used for every research study. The choice depends on the research context, assumptions, and methodology. Researchers should also remember that the formula alone does not guarantee representativeness. The sampling technique and quality of data collection are equally important. Krejcie and Morgan Table, a ready reference method. The third approach is the Krejcie and Morgan Table. Unlike the previous formula, this method does not require the researcher to perform the mathematical calculation manually. Krejcie and Morgan developed a table showing recommended sample size for different population sizes. For example, for a population of 1000, the table recommends a sample of approximately 278. For a population of 10,000, the recommended sample is approximately 370. This makes the table very convenient for students and researchers. However, it is important to understand that the table is based on specific statistical assumptions. Therefore, researchers should not blindly use the table without considering whether its assumptions match their research design or not. But now the question is how to read Krejcie and Morgan table. Let's understand. Step 1. Identify population size N, capital N. Step 2. Find the corresponding sample size small n. And step 3. Use the recommended N. For example, suppose your population consists of 1000 individuals. You locate 1000 in the population column, capital N. The corresponding recommended sample size is approximately 278. Therefore, you can use 278 respondent as the minimum sample size under the assumption of the Krejcie and Morgan table. One important point. If your exact population size does not appear in the table, you can select the next higher population value to adopt a more conservative sample size rather than simply choosing a smaller value. Let's look at a few examples from the Krejcie and Morgan table as shown in the slide. For a population of 100, the recommended sample is 80. For 500 it is 217. For 1000 it is 278. For 5000 it is approximately 357. For 10,000 approximately 370. And for very large population the sample approaches approximately 384 under the assumption of the table. This gives us an important insight. When population size increase, sample size also increase, but not in the same proportion. For example, increasing the population from 10,000 to 1 lakh does not mean that the sample must increase 10 times. This is because sample size depends on statistical precision rather than simply being a fixed percentage of the population. Important point: sample size is equal to or not equal to percentage of population. Let's understand. This is very important misconception that student should understand. Researchers sometimes say my population is 5,000, so I will take 10%, which means 500 respondent. But why 10%? Unless there is a methodological justification, selecting a fixed percentage of the population is not a scientifically sound way to determine sample size. Sample size is not simply a percentage of the population. It depends on statistical factors such as confidence level, margin of error, population variability, and research design. Therefore, instead of saying I selected 10% of the population, a researcher should provide a methodological justification for the selected sample size. Which method should you use? There is no single answer. If you have a known population and are conducting a relatively simple descriptive survey, Yamane Formula can be a practical option. Slovin's formula is also commonly encountered, although its statistical basis and original source are less clearly documented. If you need a more statistically rigorous calculation and have information about confidence level, margin of error, and population variability, Cochran Formula is a stronger choice. If the population is finite and relatively small, you can calculate the initial Cochran sample size and then apply the finite population correction. If you want a quick ready reference approach, the Krejcie and Morgan Table can be used when its assumption fit your study. However, for complex studies such as structural equation modeling (SAM), experimental design, mediation moderation model, or studies with multiple predictors, researchers should generally consider a priori power analysis rather than relying only on the basic formulas. Common mistakes in formula selection. Before we conclude, let's discuss some common mistakes. First, never choose a formula randomly just because it is popular among other students. Second, do not automatically take 10 or 20% of the population unless there is a specific methodological reason. Third, remember that Slovin's formula is a simplified approach and should not be treated as universally applicable. Fourth, do not ignore confidence level, margin of error, and population variability when using methods that require these parameters. Another common mistake is forgetting finite population correction when it is appropriate. Also, when the calculated sample size is a decimal, researchers should generally round upward, not downward, because rounding downward can result in a simple sample smaller than the calculated requirement. Finally, basic formula may not be sufficient for complex research design. Studies involving SAM, multiple predictor, mediation, moderation, or experimental group may require power analysis. Formula comparison at a glance. Let's summarize the method in one table. Method, main requirement, and best use. Slovin's main requirement n plus e, best use simple estimation. Cochran z plus p plus q plus e, best use for statistical precision. Cochran plus FPC n0 plus capital N, Best use for finite population, Krejcie and Morgan table. Main requirement is N, capital N. Best use for quick reference and power analysis is effect size plus power, and best use for complex research. Key takeaway. Let's conclude today's lecture with 5 important points. First, sample size should always be scientifically justified rather than guessed. Second, Slovin's formula is a simple approach but has limitation. Third, Cochran Formula provide a more statistically rigorous approach because it's explicitly consider confidence level, margin of error and population variability. Fourth, when dealing with a finite population, the finite population correction can be applied to adjust the initial sample size. And fifth, the Krejcie and Morgan table is a convenient ready reference method when its underlying assumptions are appropriate. Most importantly, remember that sample size determination is not just about applying a formula. The final decision should be consistent with your research design, sampling technique, statistical analysis, population characteristics, and practical constraint. So now test yourself. Question 1. Which formula uses Z, P, Q and E? Yes. What happens when margin of error decrease? And question 3. What is the purpose of FPC? So the answer of first is Cochran formula. The answer of second, the required sample size generally increase because the researcher want greater precision. And the answer of third question is adjust the sample size when the population is finite and known. If you got all 3 correct, you have understood the core concept of today's lecture. Thank you for watching this lecture on basic sample size formula. In the next stage of research methodology, we can move beyond basic formulas and discuss power analysis, effect size, statistical power, significance level, and tools such as G-power. These concepts become especially important when conducting experimental research, regression analysis, SAM, mediation, moderation, and other advanced quantitative studies. I hope this lecture has helped you to understand not only how to calculate sample size, but also how to select an appropriate method and justify your decision scientifically. If you found this video is helpful for you, then you can appreciate me by like, subscribe, and share. Thank you so much.